Hello, Express Sauce. We're sorry we can't join you in Canada, but we hope that our presentation will make a bit of sense anyway. Our paper is called Translating Concepts of the Futhark Programming Language into an Extended Pi Calculus. And who are we? We're Chris Oliver Paulsen, Lars Jensen, Julian Jørgensen Toile, and Hans Hüttel, and we're all from Denmark. Chris, Lars, and Julian are at Aalborg University, and I'm at the University of Copenhagen. Now, what we're interested in is data parallelism and how we can understand it using the Pi calculus. Now, there's been increasing interest in that topic over the last 30 years, and now the data parallel languages that we see target GPU hardware because that's easily available and not so expensive. One example of such a programming language is Futhark. It's a pure functional programming language for arrays, and it's been developed at the University of Copenhagen. And it lets us abstract away from parallel hardware in a nice way using functional programming. Now, there's also a model of computation called the Pi calculus that deals with parallel computations. It's a model for unlimited parallel computation, and it's been around for roughly the same amount of time, and it's been used for studying a wide variety of programming constructs, from functional programming, from object-oriented programming, from imperative programming, and logic programming. Now, in our work, we study how these two notions are related, because our hope is that it will give us a bit more insight into data parallel programming if we can translate this particular programming model into a model of computation, namely the Pi calculus. Now, the Pi calculus was introduced by Milner, Powell, and Walker in 1990, and it's a model for computation that uses parallel processes, parallel composition, and the notion of names is completely central, and so is name passing. Names are sent over channels, and channels are named. The central notion is the one that we see here. We've got an output. We output the name B on the channel A. Another parallel component receives on channel A a name, binds it to C, and if these two processes interact, we get P, where B replaces C. We've got parallel composition, we've seen that already, but there's also unbounded parallelism. We can use replication for that, and there's a law that says that this really is unbounded parallelism, because bang P, replicated P, is structurally equivalent to P parallel with bang P. Now, there's been a lot of work already on understanding how you can express notions of functional programming in the Pi calculus. It all dates back to the early work on the Pi calculus by Robert Milner. And name passing is crucial, and it's enough for implementing the passing of functions. And the work that we present here is inspired by some of those early results. That's the original paper from 1990 called Functions as Processes by Robert Milner, in which he shows how you can translate an untyped lambda calculus into the Pi calculus. And you can express call by name and call by value reduction strategies. 5 years later comes the paper from a concurrent lambda calculus to the Pi calculus, and it's in the context of the development of the facile programming language, and it's a paper by Amadeo and Thompson. And in this paper, the authors introduce a notion of important versus administrative transitions, and this we're going to use in our work. So the challenges that we're faced with in our work is to find out which Pi calculus to use, because there are many. And how do we describe parallel data structures in the Pi calculus that we choose? How do we prove that our translation is correct? How can we compare the forms of non-determinism found in Futhark and in our Pi calculus? How can we analyze the complexity of the processes that our translation will create? So I'm going to talk about how we've addressed these challenges. Now, Futhark is a functional array language. It's pure, no side effects. It was created by Troels Henriksen, Cosmin Wancha, and others at the Department of Computer Science in Copenhagen. It's a data parallel programming language, and the way we can manipulate data in arrays is by using second-order array combinators, or SOAKs. Now, the Futhark compiler we'll take a Futhark program and compile it into GPU code, more precisely CUDA. What we have at the bottom of the slide is a tiny example of what you can write in Futhark. First, we define an array from. And from is the array that you get by applying the soak called iota. And iota gives you an array consisting of the numbers, the integers from 1 up to 40. So that's the value of from. Now 2 has at its value what we get from mapping the function plus 65 to from. So this will give you the array containing 66, 67, all the way up to 105. Now, Futhark is an actual programming language. We're not going to study that in our work. We're concentrating on the essential features. And our sub-language of Futhark we call BUTF, Basic Untyped Futhark. It's a functional call by value array language, and it has arrays. It's got 3 soaks, and it's got tuples. In our language, we don't allow for currying. That does not really matter in this setting as far as expressiveness is concerned, but it'll allow us to give a simpler semantics, and that's important in this initial study. Here's an example of what you can write in BUTF. You can map the function lambda x, which gives you a 2-place array where both elements are x, and we can map that function into a 2-place array containing 1 and 2, and what do we get? We get an array containing 2 subarrays, the subarray 1 and 1, and the other subarray 2 and 2. So the syntax of BUTF is very similar to what we see in the lambda calculus. The new features, of course, all have to do with Futhark. We have arrays, and they're here. We can look up by indexing some element of an array. We do that here. So we take an array whose value is the value of E1, and we look up the index whose value is the value of E2. We've also got tuples. We've got them here. And then, of course, we need to have values as well. We've got integer constants, we've got arithmetic operators, plus and times, and we've got the 3 soaks, map and size, which tells us the size of an array, and iota that we've just seen. Now, the semantics of BUTF uses a call by value semantics because we want to stay faithful to Futhark. And parallelism appears in computations on arrays in the sense that because this is a pure language, if some cell in the array evaluates, the entire array evaluates, and there's non-determinism creeping in because it's not specified in which order you evaluate the cells of an array. Now that's our version of Futhark. How about the PyCalculus? Well, our PyCalculus contains all the usual favorites from the PyCalculus: action prefixing, parallel composition, name restriction, and replication. So that's all just as it was in the days of Robin Milner. And the semantics is also quite standard. We use a reduction semantics. We use structural congruence that allows us to rewrite process expressions and alpha convert if need be. Here are some examples of what you can do using structural congruence. You can extend the scope of new A to cover this process, and you can unfold this replication and get another parallel component. And the reduction rules describe what communications do, and we saw already an example of communication. So here's the communication rule, and the reduction rules interact with structural congruence in the sense that structurally congruent processes have the same reductions, which is what the struct rule says. Now, that's completely standard PyCalculus, but we need to be able to express a bit more than that. We need to be able to express the essential aspects of array computations. So we must be able to send data values, such as numbers, and arrays, and we use the constructs of the applied PyCalculus by body, so we can write things like on the A channel output the value of 2 plus 2. And because we need to receive data values, we must have variables that we can instantiate, so we distinguish between variables and names. Moreover, sometimes we want to be able to query an entire array, all cells in the array at the same time. So in order to be able to do that, we allow for broadcasting. So we can broadcast on channels as well, and this is something that came about in the work by Ina and Montian, and later was studied by Hüttel and Process. And this is the notation that we use. A colon B means that on channel A we broadcast B to possibly lots of recipients. And moreover, because we want indexing, we use polyadic names, so names can be composite names. So what we have here says that we actually want to look at the cell with index 4. That's the idea. So that's what we need to extend our PyCalculus with. So now we can translate BUTF expressions, given what we have, and the translation is inspired by previous work by Robin Milner and Amadeo Thompson and Thompson. And the translation of expression uses what we call a result channel that we use for transmitting the return value of the expression. We write E in parentheses O. And functions have handle names. That's what we use for getting access to functions. And we use the result channel for communication, and when we translate lambda abstraction, we see that here we set up a new function name and we transmit that to the world on our result channel, and then everybody can use us by using the f name. And because we can use the function as many times as we want, this resource needs to be replicated, what we see here. But we're not going to talk about these completely standard features of the lambda calculus. We're going to focus instead on the translation of arrays. Now, here's one way of thinking about it, because if we have an array with 3 places that contain the elements 4, 1, and 0, how could we express that? We could have an output channel for each cell on which we can transmit the index of the array and the value stored in that particular cell in the array. And then if we want to interact with that particular cell, we simply use the O channel, because we need to share that handle among everyone, and we use the index for the first component for getting the right cell. But this sort of array can only be used once. How do we deal with that? Well, if we want to be able to have persistent arrays, we need to use replication, and that's what we do. And if we want to be able to query all elements of an array at the same time, we use broadcasting and a special name we call all. So a cell we see here can be used as many times as we want, and we have a handle h and we have an index I, so getting access to the array at I we're allowed to do that if we use the composite name h.I. And if we want to get hold of all elements in the array, we use the composite name h.all. And if we have an array as a result, we return its handle on the result channel, just like we do with abstractions. We use the result channel to return the value of an abstraction. Now, if we want to use the soaks, how do we do that? Well, here's an example of that. Let's suppose we want to map the function +1 to our array that we just saw. What do we do? Well, first we query the array, and then when we get the values back, we set up a new cell with the same index and a value to which we've added 1. So we use the A channel, the array channel that we set up for this interaction. And we create a new array. And we use replication for that, of course. And sometimes we want to communicate with a particular function. We don't see that much here. We write just +1, but we need to use the function handle to deal with that. I won't describe that here. The Futhark language is called by value, and so is BU2F, so the translation must be able to express that. So what we do is that we make sure that if we want the value of an array, we can only get that once the array has been fully evaluated. All cells have been made. So we use a special name called done for saying now we're done. On that name, the done name, we communicate. So that's the idea behind that. Now, a few words about the translation. Why is it correct? Well, we know from other encodings into the Pi calculus that the original term that we're encoding and its translation don't have the exact same behavior, because one step by the original expression may require several steps by the translation in order to be simulated. So what we do here is we distinguish between the actual steps and all the administrative steps that we need to set up the actual step. And the steps that are that correspond to actual computation are what we call important. And in our translation, we can place a dot at the point where we say, oh, there's something important going on here. And all of the steps that just shuffle things about in order to set up a computation, we call them administrative. And important steps are marked with the black bullet, and administrative steps are marked with the white bullet. An example of where things get important are in the encoding of a function application, E1 applied to E2. It's only at the very end that something important happens, namely here. The function handle is being sent. Now, how do we translate map? We saw an idea of that, how that was supposed to be done. Now, suppose we want to translate map of E1, where E1 is supposed to be a function. What do? Well, we translate E1, and then we have result channel O1. We set up a result channel on which we can receive the arguments, and we set up the external values. We set them up here, and then we set up a counter name that we use for making sure that all cells of the array have been processed. We create a repeat process that handles the repeated application of our function E1 to all elements, and then this is where the actual function application takes place. And after that, we can then aggregate the values that we found into a new array, which we build here. And then, once we've done that, we're done, and we use the name done for that. We've seen that before. This is where that happens. And note the red dot here. The red dot says that this is where computation, the actual computation, has finished. All the other previous communications in our Pi calculus process all had to do with setting things up. Now, those are some of the features of our encoding. And how do we prove that the encoding is correct? Well, we need a notion of semantic equivalence. And we use a form of weak bisimulation, also known as delay bisimulation. We speak of weak administrative bisimulation, or WAP. I will not give you the formal definition here, but the idea is that a relation is a WAP if whenever two processes P and Q are related. And if P can take an important transition, then Q can do some administrative steps, but then finally it does an important step, and Q prime and P prime, the results are still related. And if P can do an administrative step, then Q can follow that by administrative steps, and we're still related. And moreover, semantic equivalence must be preserved in any context, and we allow for the same initial actions, the same barbs. And we write P double tilde A Q if P and Q are related by some WAP. So this is semantic equivalence as we almost always see it in a process calculus. But we also use a similar notion for proving the correctness of our translation. We match steps, BU2F, with steps in ePi, and what we match are important steps. So relation between expressions and processes is what we call an administrative operational correspondence. If the expression can perform a reduction step, then P can actually, the process can actually perform an important transition sequence. Maybe there's something administrative going on, but there's something important going on, and after that we are similar or bisimilar to something that is related to E prime. And conversely, if P can perform an important step also with some administration involved perhaps, then E can answer back by becoming E prime, and E prime is then related to some Q, which is bisimilar to P prime and is found in R. So with this notion, all we need to do to prove correctness is to simply build a relation which is an operational correspondence, and then the idea is that our operational correspondence relation consists of expressions and their translation, and we then prove that R is an administrative operational correspondence, that it satisfies the conditions of the definition. I don't have time for that, it's a rather large case analysis, but it can be done. So one last thing that we wanted to address was how can we analyze the complexity of what's going on. I won't talk about that in any detail here, we don't have time for that. But there are two notions of complexity analysis that are important in the setting of parallel computation, and those are work and span. And the work of a parallel computation counts the actual instructions that happen, and span measures the depth of the parallel execution. So suppose we wanted to compute 2 to the 8th. Then if we did that sequentially, we would have 7 multiplications. The span would be 7. If we did this in parallel, we would have 3 levels of parallel execution. First, you multiply 2 by 2 repeatedly, you multiply 4 by 4 repeatedly, and finally you multiply 16 by 16. So those are 3 levels of execution. So here the span would be 3. So if we want to carry out such a complexity analysis, what would we view as an instruction? Well, we would view all the places that are marked by black dots, because those are the actual instructions, the important steps. So one can do that, and we have more details about that in the paper. Let me finish off by saying what we found out. Well, what we did was we studied BUTF, a non-trivial subset of the Futhark language, showed that you can express it in ePy. The translation that we've come up with is correct. We proved that using a co-inductive technique that looks a bit like bisimulation. And we can actually, as it turns out, study the complexity of our translation using the annotations that we have. What next? Well, there's divergence, and you can diverge in a translation, and that's a common problem. How can we deal with that? If we want to deal with that, we should probably have some notion of equivalence or operational correspondence that involves divergence. Then there are types, because Futhark is typed, but BUTF is by definition untyped. Suppose we had types or sorts, what would a translation look like and what properties would it satisfy? Then we introduced the applied pi calculus and broadcasting, and we introduced polyadic names, and one might ask, do we really need those to make this translation work? It's already known that these process calculi are different from the pi calculus in terms of expressive power, but one should still ask this question. Can we do without and still get a nice and meaningful translation? We look at call by value. What if we looked at, say, call by name, or looked at evaluation strategies for arrays? How would that impact the translation? Finally, I glossed over complexity analysis quite a bit. And one might argue that the form of complexity analysis that we've chosen is imprecise. How can we get a better analysis of complexity? Now that's the end of our presentation. Thank you for watching.